Okay, so let's talk about state functions. So when we talk about the term state in this context, in the context of thermochemistry and thermodynamics, we're referring to its exact condition at a fixed instant. Now, I'm quite sure that we have met, or you have met, the term state in relation to the phases of matter, solid, liquid, and gaseous state. Well, in thermochemistry, it's a bit more than just that, all right? The state in this context is determined by several things, as you can see here on the screen, by the kinds and amounts of matter that is present in the system, the structure of this matter at the molecular level, and the prevailing pressure and temperature. All right, so basically, you can even have a change of state within the same phase. Let me just kind of sidetrack a bit and move on to an example. So let me get out of this here. Okay, so let's say, for example, get out of this. Okay, so let's say, for example, you had H2 gas at, let's say, 1 atmosphere. And let's say that you change the conditions so that H2, the same gas, will now have a pressure of 2 atmospheres. All right. Well, this is, even though it's a gaseous state to begin and end with in this process, by virtue of the fact that the pressure changes, we're talking about a change of state. All right. The state of the hydrogen gas has changed simply because you have changed the pressure. Let me give another example. Let's say you have iron, which is a solid, and let's say that you had it at a temperature of 50 degrees Celsius. And let's say that you increase the temperature from 50 degrees to 70 degrees Celsius. Well, this is also another example where there's a change of state, simply by virtue of the fact that you have increased the temperature. So change of state basically means that you have changed the conditions, which will result in changes at the microscopic level, because in each case, in each of the examples that I pointed out here, the way the molecules will behave at the different pressures or temperatures will be different. All right. In the case of the gas here, if you increase the pressure, that means that the molecules will be colliding with the walls of the container more frequently, exerting greater pressure. So as you go from 1 atmosphere to 2 atmospheres. So therefore, there's a change of state associated with that change. And similarly, in the case of the iron example that I used on here, change in temperature, means that the change in the amount of energy that the particles of iron will have will occur, and therefore, as a result, there's a change of state. So those are just two simple examples just to illustrate what we mean by the term change, well, the term state in the context of thermochemistry. So let me go back to what we were discussing here. Now, associated with a state, we have what are known as state functions, right? And as stated here, a state function is a quantitative property that is uniquely valued that depends on the state of the system. And it does not depend on how the state was reached. In other words, it does not depend on the history of the system, all right? And there are several state functions that we're going to meet shortly. And this leads us now to the first law of thermodynamics, also known as the conservation of energy law. And this law says that in a physical or chemical change, energy can be exchanged between a system and its surroundings, but no energy can be created or destroyed. Okay, so let's spend some time talking about this first law in some more detail. So to summarize, basically what this law says is that energy cannot be created nor destroyed in the universe. And one inference of that is that the internal energy change of a system is a difference between the energy between its final and initial states. So in other words, the change in internal energy represented by delta U is simply the difference between the final internal energy that the system has minus the initial internal energy. Now, another additional inference we can come to based on the first law of thermodynamics is that if the energy change occurs only as heat and or work, then the change in internal energy that we talked about here, delta U, will be equal to Q plus W. Q is the amount of heat added to the system, and W is the amount of work that is done on the system. So basically, those two added together will give you the change in internal energy. Now, in some textbooks, in fact, in nearly all textbooks, this equation here is actually a mathematical expression of the first law of thermodynamics. So, in other words, the first law of thermodynamics can be stated in the words that we had in the previous slide. Let me just go back to it here. Right, so this statement here is the first law of thermodynamics, but mathematically speaking, we can express the first law of thermodynamics using this equation, because we get to this equation from inferring two facts from the first law of thermodynamics expressed in words. Now, whenever you're using the mathematical equation which represents the first law of thermodynamics, it's very important that you use the appropriate signs, especially when you're given a question where you need to use that equation to solve that problem. So here's what you need to be cognizant of. Whenever you have energy entering a system, right, then that energy value carries a positive sign, all right? Now, there are two ways that can happen. If heat is absorbed by the system and or if work is done on the system, right? So if you're heating a system, then basically the energy entering the system due to the heat added will be positive. And if you're doing work on the system, then the energy entering the system would be positive as a result of the work done on the system. And if that is true for situations where energy is entering a system, then the opposite is true when energy is leaving a system. When energy is leaving a system, that energy carries a negative sign, right? So if heat is given off by the system, then that would be seen from the system's standpoint to be negative. If work is done by the system, again, from the system standpoint, work would be negative, and therefore, in both instances, energy would be leaving the system, which means that as far as the system is concerned, its change in energy would be negative. Okay, so here is a simple example which illustrates the appropriate use of signs when it comes to using the first law of thermodynamics expressed mathematically here. It says a gas does 135 joules of work while expanding, and at the same time it absorbs 156 joules of heat. What is the change in the internal energy? So in this case here, this is the equation you're going to use. Delta U is equal to Q plus W. So you have to read the question carefully to see what signs you'd use for both the work and the heat. Now, of course, you have to look at how the question is worded. So the very first line of this sentence, of this question says, a gas does, and I want to emphasize does, 135 joules of work. So what that means is that from the system standpoint, the 135 joules will be negative. So W here, work, would be minus 135 joules, right? So it says a gas does 135 joules of work while expanding, and at the same time, it absorbs 156 joules of heat, which means that, again, from the system's standpoint, if it's absorbing heat, that means that the heat is positive. So therefore, in this case here, we put 1 plus 156 joules for Q. And then we do the simple math, and we end up with the answer to the question, which in this case is 21 joules. All right? So this is a simple example, but this underscores the importance of reading the question carefully so that you can interpret it correctly with respect to the sign that is used for the Q term and the W term. Okay, so let's look at heats of reactions. So when we're talking about heat of reaction, we're talking about the amount of heat that is exchanged between the reaction system and its surroundings. And in this context, there are two types of reactions. You have what is known as an exothermic reaction, which gives off heat. In an isolated system, what that means, therefore, is that the temperature of that system will increase. And what that also means is that as far as the system is concerned, it goes from a higher to a lower energy state. And as a result, Q reaction, the heat of reaction, is negative, okay? Then we have the opposite, which is the endothermic reaction, which is a reaction which absorbs heat. Now, in an isolated system, in that case, the temperature would increase. And what this means also is that the system goes from a lower to a higher energy, which means that Q reaction is positive. So just to give you some practical examples, if I were to say add some sodium hydroxide to a test tube with water, and if you were to feel the outside of that test tube, then basically that would be an example of an exothermic process, because as the sodium hydroxide is going into solution, heat energy is liberated, all right? So therefore, the Q reaction, if you were to calculate or measure the Q reaction, then you'll see that it's negative. On the other hand, an example of an endothermic process would be if you dissolve potassium nitrate in water. In that particular instance, if you do that in a test tube, then, and you feel the outside of the test tube will feel cold. And the reason why that happens is because the reaction as it progresses, or the process as it progresses, absorbs heat from its surrounding. And therefore, in this particular case, Q reaction will be positive. Okay, and this diagram here basically illustrates what happens in the case of an exothermic reaction if you did that reaction in 3 different situations. Now, this example here, this reaction vessel here to the left, is basically a purely hypothetical situation where, let's say, the reaction is exothermic and heat is generated. In this particular case, all the heat that is generated will be given up to the atmosphere, to the surroundings, which is very, very unlikely to occur, right? If that were to happen, then the temperature at the end of this process would be 25 degrees Celsius, which would be the same as the temperature of the surroundings, all right? But this is purely hypothetical, all right? Not likely to occur. What is more likely to occur is this right here, where some of the heat generated in an exothermic reaction will be given up to the surroundings, and the rest of it will be basically absorbed by what is left in the reaction vessel, and as a result of that, the temperature increases to a value above the surroundings temperature, in this case 32.2 degrees Celsius, all right? This is, as I said before, the most common situation that is likely to occur. And then now, in the case of an isolated system, such as what you see here, which is basically 2 styrofoam cups where you put the reactants in and the reaction takes place. In this case, unlike this case, no heat is given out to the surroundings. So therefore, when the heat is generated, it's absorbed by whatever is left inside the vessel. And as a result, the temperature increases to a value which is higher than the previous example, all right? Okay, so that's what happens in these situations, in the case of an exothermic reaction. And if you understand this, then you should be able to understand why, or what would happen in the case of an endothermic reaction. Okay, I won't go into that, but I'll leave you to figure that out. If you have any questions about it, feel free to call me. All right, we're going to stop here for this video, and the next video will be starting off with a discussion of change in internal energy under different conditions. So that's it for now.